Hi, my name is dr. Ahmath. In this video lecture, we are going to talk about really important theorems on the vectors. So all of them are really important because they are going to help us to build up more advanced theories and topics in this course. So first, I'm going to discuss about the Pythagoras theorem. So we know this from the school, but this is going to be the version of this theorem for the high dimensional vectors. In any dimension. So later on, we're going to talk about so-called Cauchy-Schwarz theorem, which is like one of the interesting and useful theorems in any course about the vectors. And also, we're going to talk about the triangles inequalities. All of these theorems are really useful. We're going to use them many times during this course. So before we start talking about the first theorem, so let me just like remind you what we've discussed in one of the previous videos, where we have found the angle between the two vectors, the cosine of the angle between the two vectors is going to be equal to the u transpose to the v divided to the norm of the u and the norm of the v, right? And at the same time, if the angle between the two vectors is equal to the pi over t, if the angle between the two vectors is pi over t, then we call this vectors as orthogonal. And we can quickly check whether two vectors are orthogonal or not by just checking whether they are inner product or the scalar product is equal to the zero. Right? So this is what I would like to just remind you. So let's first of all start with the Pythagoras theorem. Pythagoras theorem. So theorem Pythagoras. So let u and v are two n-dimensional vectors, and they are orthogonal. They are orthogonal. Then the following theorem holds, like a u plus a v, its norm in the square is going to be the norm of the u in the square plus the norm of the v in the square. So I would like to draw the three vectors so that you can imagine what we're talking about here. So if you remember that if I would like to add two vectors, I need to put the second vector to the end of the first one, right? So let's say we are given the first vector u, right? And the second vector v is given like this. So at the same time, they are given that it is given that they are orthogonal, right? So the angle between of them is 90 degrees. So I just would like to copy this v vector to the end of the u vector. So let me try to copy this in a better way. So this is going to be the v vector, right? And the addition of these two vectors is going to be this vector, which is going to connect the starting point of the u and the ending point of the v. So this is going to be u plus v. So basically, we've got a triangle with a right angle, right? And if you remember the Pythagoras theorem in school, it was like a hypotenusis of the triangle is equal, and the square is equal to the sum of the squares of the sides, right? This is what we have here as well. Like a u norm in the square, v norm in the square is equal to the u plus v norm in the square. Okay, so this is the image so that you can understand what we're talking here. So in order to prove this, I'm going to use this equation here. So let's try to prove this. So it's really important for us to learn how to prove this kind of theorems, because the idea of expanding the norms, for example, is the same for all kinds of exercises and the theorems. So let's try to prove this. So the norm of the u plus v in the square can be expanded as a matrix multiplication. So if you remember, so this is one of the really important equations. Like the norm of the u in the square is equal to the u transpose to the u. So basically, the length of the vector in the square is just the multiplication of this vector to itself as an inner multiplication. So I'm going to rewrite this. So the length of this vector in the square is equal to the multiplication of the u plus v to itself, to the u plus v. So I'm just going to open up all the brackets. So it is going to be u transpose to the v transpose times to the u plus v. Then I can open up the brackets. It is going to be u transpose to the u plus u transpose to the v plus v transpose to the u plus v transpose to the v. So if you remember, the theorem states that if they are perpendicular, right? So it is already given that they are orthogonal. So that is why U transpose is a V and V transpose is a V, and U transpose is a V and V transpose is a U are equal to the 0, according to this equation, which we had before. Okay, so that is why what we have here is simply U norm in the square, because so this is equal to the norm of the U in the square, and this is also equal to the V norm in the square, plus V norm in the square. So that's it. So the proof is like really short and elegant. Okay, but you need to imagine what we're talking here. So let's talk about another theorem, which is a little bit more difficult to understand. So let's talk about this theorem, Cauchy-Schwarz. So it basically tells us that, hey, if you are given t vectors, but U and V are t n-dimensional vectors, then for these vectors, we've got like a U transpose is a V, which can be a negative number as well, right? And the square is less or equal than the norm of the U in the square and the norm of the V in the square. If you basically take the square roots from both of the sides, that's going to be the absolute value of the U transpose is a V is less or equal than the U norm times the V norm. So please note again that the multiplication of the U to the V can be a negative. So that is why whenever we are taking the square root, it is better to put the absolute values. Okay, so I'm going to show you like two proofs here. So one is going to be a little bit more theoretical, but the second one is going to be more intuitive. So let's start from the theoretical one. So the proof. Okay, so let's have a vector like a U minus KV. Okay, so you're given two vectors, and I would like to find this vector. So this is obviously going to be as well a vector. So what I would like to do is I would like to find this length of this vector, where K is any constant. Okay, so constant. So I would like to open up the brackets. So if you open the brackets up, it's going to be U transpose to the KV, sorry, minus KV transpose, right? Because we've just learned how to do this previously. So times there's a U minus KV. So please note that whenever you transpose the constant, right? So if, for example, you're given 3, if you just transpose this, it's going to be, again, 3, right? Because just like transposition means like you're writing down the row as a column, row, and columns as a row. So I would like to open up the brackets. It's going to be U transpose as a U minus K U transpose as a V minus KV transpose is a U plus K squared and V transpose is a V, right? Okay, so let me simplify everything out. It's going to be the norm of the U in the square minus K U transpose is a V, right? So times T to the 2 as well, 2K. Because please note that this is the same as this one. This 2 multiplications are the same. So it is going to give you the same result, essentially. So the plus K squared times the norm of the V in the square. Okay, so no matter what is the K, the value of the K, so this norm in the square is always positive, right? So the norm of any vector, the length of any vector is positive, and the length in the square is also positive. So this is a positive number, so non-zero number. Okay, so is that clear? For any value of K, so it doesn't matter what you choose for the K, it is always positive. Let's choose the K a specific value. For example, I can choose the value of the K as the U transpose the V divided to the norm of the V, okay, in the square. Since this is true for any value of the K, it is true for this value of the K as well, right? So let's just substitute everything. So I'm going to just substitute the K to here. It's going to be like U norm in the square minus 2 times U transpose the V divided to the V norm in the square times U transpose the V, right? So plus So if I'm just going to substitute this to here, it's going to be u norm to the v. It's a constant divided to the norm of the v in the fourth power times the norm of the v in the second power, right? So let's simplify everything out. So it's going to be the norm of the u in the square minus. So please note that this term is the same as this one, right? So it's like minus 2 multiplied to something plus the same thing, because you can just cancel out this terms, right? And they are the same. So it means that I can just write this down as a u transpose to the v in the square divided to the norm of the v in the square, and this is still positive. So do you remember here, we've got this expression, which is always positive for any value of the k. No matter what is the k, you can choose infinitely many values for the k, and it's still going to be a positive. So we've decided to choose a specific value for the k, and it still should be positive. So I'm just going to put this term to the right and try to simplify the terms out. So it's going to be the norm of the u in a square. It's more or equal than u transposes a v in the square divided to the norm of the v in the square. So I can just multiply both of the sides of the inequality to a positive number without changing the inequality sign. So it's going to be the norm of the u in the square times the norm of the v in the square is more or equal than the u transpose to the v in the square. This is what we needed to prove actually, right? So this is going to be always the positive. So this is going to be always the truth. So this is the theorem of Cauchy-Schwarz. This is what we wanted to prove. Okay. Well, there is the proof might be a little bit more theoretical, but it's quite elegant. And this is using the same technique which we have here. It's basically the most important part for me, at least, most important technique I would say, is just expanding the vector's norm in the square. So this is the important part. So there is a more intuitive proof of the theorem. So if you remember, the cosine of the angle between the two vectors is equal to the u transpose to the v divided to the norm of the u and the norm of the v. At the same time, we know that the range of the cosine is always between -1 and 1, right? So no matter what is the theta, the cosine of the theta is always going to be between -1 and 1. So basically, I've got a 3 terms of this inequality, and I'm going to multiply all of the 3 parts, this part, the middle part, and the right-hand side part, all of the 3 parts with a positive number, which is going to be the norm of the u and the norm of the v. Let's multiply all the 3 parts with a positive number. So in this case, I will get the negative, the norm of the u, the norm of the v, less or equal. So in the middle, they are going to be canceled with the denominator, right? And what I will have here is the norm, so v transpose multiplied to the u, and this is less or equal than the norm of the u and the norm of the v. So which can be collapsed, right? So this is the expanded version. So I can just collapse this into a more a compact form. It's going to be the module of the, or absolute value of the u transpose to the v is less or equal than the norm of the u and the norm of the v. Okay, so this inequality with the 3 sides is equivalent to this one. So if you remember, we've learned previously in a high school, for example, if you're given this kind of inequality, the norm, the absolute value of the x is less or equal to the 3, what does it mean? It means that x can be any value between -3 and 3, right? So basically, in the number line, you can choose any value between -3 and 3, any value, right? And this is going to be true here. So you can just substitute -2, -3, -1, or +1, +2, +3 to here, and these 2 things are equivalent. So this is what we did here, right? So if you just eliminate the absolute value symbol, then you're going to get this inequality with the 3 sides. Okay, so this is the second equation here. Both of the proofs are valid, actually. So let's try to prove the last theorem. So this is the triangles inequality about the vectors So theorem, triangles, inequality. So it basically states that, hey, we're given two vectors u and v in n-dimensional space. Then the u plus v norm is smaller than the u norm plus the v norm. Smaller or equal, right? So because we know at least one case when they're equal, right? So this is equal. So when the angle between of them is 90 degrees. Okay, if you remember in the school we had a similar triangular theorem as well, right? So you can just basically imagine that you've got the two vectors. This is going to be u, this is the v, and this is going to be the sum of the two vectors, u plus v. And the theorem states here that the sum of the two sides, u plus v, is always bigger or equal than the third side. Okay, so if you just sum the length of this side plus the length of this side, it's going to be longer than this side always. So this is what it states. So I'm going to try to prove this theorem. So again, as I told you, the most important technique which you need to learn from this lecture is how to expand the vector's norm in the square. So let's say you are given a vector's norm. So this is the u plus v norm in the square. Okay, so it's difficult for us to expand just the norm, but it's easier for us to expand the square of the norm. So the norm square is equal to the u plus v transpose to the u plus v. Okay, so the norms in the square is going to be the vector times the vector as an inner product. So I'm just going to apply the transpose to the first bracket. It's going to be u transpose plus v transpose times the u plus v. So I'm just basically going to expand everything out. It's going to be u transpose to the u plus 2u transpose to the v plus v transpose to the v, right? So at the same time, it is equal to the norm of the u in the square plus u 2uv u transpose to the v plus the norm of the v in the square. Okay. So at the same time, please note that the u transpose to the v is an inner product of the two vectors, or it's basically the scalar product. And this can be a positive value, but at the same time, this can be a negative value. So it can be positive, negative, it can be equal to the 0, right? But at the same time, so what I can do is, so if I would just write this down as a u norm in the square plus 2, and then its absolute value, u transpose to the v plus the norm of the v in the square, then which one of them is bigger, or are they equal? So obviously this part is going to be bigger, right, or equal, because I'm taking only the positive part of that. But since this can be negative as well, so if I just put the absolute value, then it's going to be positive. It's going to be bigger, okay? So this part is bigger, right? So it's clear. So at the same time, we've got a Cauchy-Schwarz theorem. So Cauchy-Schwarz theorem, which states here that the u norm, u transpose to the v and its absolute value is smaller, equal than the norm of the u times the norm of the v. Okay, so it means that this term, basically the second term, is smaller than the following one: the norm of the u in the square plus 2, the norm of the u, the norm of the v, plus the norm of the v in the square. So it's smaller than this, let's say number 3, because of the Cauchy-Schwarz theorem, right? Because this term is smaller than this term, so that is why this 2 is smaller than 3. So at the same time, I see that the 3 can be, again, collapsed into the smaller compact form. So I can write this as the norm of the u plus the norm of the v in the square, right? So what I got here, actually, so do you remember what we've started with? So we started from this term, right? And this is going to be, this term, 1, is going to be smaller than this one, let's say 4, right? Obviously, because I expanded 1 to something, then I substituted this thing with this 2, right? I said that, hey, 2 is bigger than that thing, and 3 is even bigger than 2, then 4 is equal to the 3, actually. So that is why, consequently, 1 is obviously going to be smaller than 4. So I've got like a u plus v norm in the square is smaller or equal to the u norm plus the v norm in the square. So I can quickly eliminate the squares, and what I will have here is u plus v norm is smaller than the u plus v norm. And I can do this I can do this easily, simply because all of the numbers here involved in this side and in this side are positive numbers. Well, this is it about like the most important theorems on the vectors. Thank you.